Hey Guy, today we will delve into the life of a great physicist. Albert Einstein was a German theoretical physicist of Jewish descent, recognized as one of the greatest physicists of all time. He developed the general theory of relativity, one of the two pillars of modern physics. Let's immerse ourselves together in the art of music and the story behind his life. Listen to the entire story, and if you enjoy it, please like, share and subscribe to the channel to hear more great stories. On a gentle evening in March 1879, as the faint oil lamps began to flicker in the wood-panelled rooms of the city of Ulm in southern Germany, a small cry echoed through the house at number 16 Bahnhofstrasse. The child was named Albert, as his mother affectionately called him, and from his very first moments, his destiny was intertwined with the profound silences of thought and an unending curiosity. His father, Hermann Einstein, a modest engineer and businessman, and his mother Pauline Koch, a woman with an artistic soul, welcomed their firstborn son with simple, warm joy. Albert was born into a Jewish family, not especially wealthy but always filled with love and a passion for learning. In Ulm, where breezes from the Danube River drifted through narrow streets, the Einstein family's life consisted of busy days trading electrical components and small machinery. Hermann and his brother Jakob Einstein had established a small workshop producing electric lamps and measuring instruments, but the business struggled. The market was fiercely competitive, budgets were tight, and the new technology still held many mysteries. Meanwhile, Pauline Koch, though not a mathematics enthusiast, always soothed Albert with warm piano pieces and mythical stories of her own creation. The little house was filled with the alternating sounds of her playing and the gentle hum of basic arithmetic. She would play lyrical melodies. Albert would listen, then call upon her to explain why those notes sounded as they did. It was during those evenings that the boy began to perceive the link between sound and number, between rhythm and distance, a faint spark that would later light his love of science. When Albert turned 3, the family moved to Munich, the capital of Bavaria. At that time, the city was coming to life beneath the silhouettes of power plants and the first urban tram stations. Each morning, little Albert would sit by the window of their apartment on Krautergasse, watching the yellow trams glide slowly past. The gleaming rails and the overhead wires draped across intersections made him constantly ask, "Mother, how does the electricity run like that?" But his mother's answer, "There are invisible currents flowing through the metal wires," only partially eased the deep-seated curiosity within him. At the age of 5, Albert began carrying his satchel to his tutor's home. On his first day at Luitpold Elementary School in Munich, the boy, with his wide eyes and tousled hair, stood silently as numbers and letters danced across the blackboard. His classmates cheered, but Albert simply studied each white chalk stroke on the dark stone surface. The headmaster noticed his quietness and asked whether he understood the lesson. Albert only shook his head, then lowered his gaze. After class, the headmaster handed him a small copper compass. "Try drawing a perfect circle," he said. Albert looked up, feeling a curious excitement. His small hand placed the compass on paper, gently turned it, and a slender yet even circle appeared. That sensation, the precision, the harmony of geometry, etched itself into his mind as if each circle were an answer to the universe's questions. Yet in the rigid order of school, young Einstein did not always fit in. He showed little interest in Latin or classical poetry. Instead, mathematics and geography were his passions. Sitting by the classroom window, Albert often daydreamed that he was releasing a paper airplane over a vast field, adjusting its wings, calculating lift and wind direction. One day he crafted a flying toy model using popsicle sticks, notebook paper, and thin wire, a simple creation that flew several meters before landing. When his teacher saw it, rather than reprimanding him, he simply smiled. Sometimes, curiosity leads us to unexpected things. The Einstein family, though at times facing financial hardship, always made it possible for Albert to cultivate his interests. In 1881, when he had just turned 2, his mother sewed him a small birthday cake. decorated with the numeral 2 set into its base. She explained that each numeral represented 1 year, and that Albert needed to continue calculating many new things. Those gentle words imprinted themselves deeply on his mind. Each added year was a number. Each number was an idea. By 1885, when he had just turned 6, Einstein began learning the violin at his family's suggestion. Pauline believed that music was the language of emotion and would help Albert balance reason with imagination. In the small room, sunlight filtered through thin curtains, the window ajar letting in the rustle of leaves. As Albert stretched the violin strings, sounds not yet in tune, but containing the longing to perform magic. With each awkward note that rang out, he came to understand that everything in the universe, whether a number or a musical note, followed a law, and that humanity's role was merely to observe and discover. Albert Einstein's childhood passed in the warm embrace of his family, interwoven with the clatter of machines in his father's workshop and the gentle music of his mother. The boy grew up with unanswered questions, yet also with the conviction that, with enough patience, each answer would gradually reveal itself. In that tranquility, where small streams meandered through the heart of the city, the seeds of a genius began to sprout, quietly and persistently, like the breath of the night. As evening shadows lengthened and the pale streetlights illuminated the damp alley, Albert would often sit with his sister Maya, who would later become his steadfast companion, and read science fiction stories. The two siblings were enthralled by tales of stars, voyages to the moon, and the invisible laws governing all things. The yellowed pages and primitive illustrations did nothing to hinder their imagination. On the contrary, each sheet of paper was a door to the vast universe. And so, in those simple yet curiosity-filled early days, Albert Einstein laid the first stones of his journey to uncover the natural laws. His life's current began in a small town, within an ordinary family, where mathematics and music intertwined, and where questions and silence coexisted. He could not have known that one day not far off, he would write the theory of relativity and change humanity's view of space and time. But here and now he was merely an inquisitive boy, enchanted by perfect circles, delicate musical notes, and dreams soaring beneath a starry sky. After the years filled with memories in Munich, the Einstein family moved once again, this time to Luitpoldstrasse, where Hermann expanded his electrical equipment workshop, and Pauline took on piano teaching at home. Albert, now older, began to show his own distinct personality. He diligently read extra books at the little bookstore nearby, tackled advanced math problems beyond the school curriculum on his own, and occasionally conducted simple chemistry experiments in the corner of the kitchen. However, the increasingly strict discipline of the school environment felt confining to him. In the Latin class at Luitpold School, Albert hated having to memorise dry grammatical structures and mechanically complete writing exercises. He would often rest his head on his desk, his hand flipping to another page, pages about mechanics, electricity, and elementary calculus. One day the homeroom teacher discovered a copy of Primitive Analysis in Albert's desk and confiscated it, demanding an explanation. Albert was silent, then simply said, "I want to understand why, when two forces combine, the result is not merely their simple sum." The headmaster frowned, reminded him to focus on the core subjects, but inwardly, he too was puzzled by this student. At that time, Einstein became acquainted with non-Euclidean geometry through the introduction of a family friend, Dr. Max Talmud, a Polish-born Jew who would visit the Einsteins on Friday evenings for the Sabbath meal with Pauline. Max brought with him the most modern science books, from Helmholtz's Introduction to Electrodynamics and Magnetism to Max' The Principles of Mechanics. Albert devoured every page and frequently posed profound questions. Why does light carry no electric charge? Or, what is the true nature of gravity? Max looked at him with encouragement and advised him to read Kant as well, in order to form his own views on space and time. At the age of 12, when his peers still enjoyed playing hide and seek or cuddling stuffed animals, Albert built a small Galton board apparatus with his own hands to control the motion of rolling beads on an inclined plane, noting the click-click as they collided. He meticulously recorded every parameter: the angle of inclination, the mass of each bead, the coefficient of friction. From these observations, he derived the relationship between acceleration and applied force. When his parents saw the homemade Galton board strewn across the living room, they initially worried about its danger, but after Albert explained how he had installed safety guards, they felt reassured and let him continue his experiments. In 1888, the Einstein family encountered a financial crisis. Hermann's electrical equipment workshop ran at a loss, and debts to the bank mounted. Within a year, Pauline was advised to leave Munich so that the children could study in a less competitive environment. In November of that year, the family decided to move to Zurich, Switzerland, where education was more liberal, and they hoped to find a fresh start. Upon arriving in Zurich, Albert had just turned 9. He enrolled at the Cantonal School under the oversight of Rector Adolf Gresser, who immediately recognised his extraordinary mathematical talent. In his first examination, Albert flawlessly completed every problem in analysis and geometry, then began studying the advanced mathematics curriculum for secondary students. He was granted permission to borrow from the Cantonal Library texts, such as Introduction to Partial Derivatives and Lectures on the Mechanics of Rigid Bodies. His peers regarded him with a mixture of admiration and apprehension, for though he was only in 9th grade, he already grasped concepts that many university students found perplexing. However, the difference between passion and discipline was not always easy to reconcile. Albert frequently skipped lessons that did not interest him, and though his grades were good, they did not fully reflect his enormous potential. Once, when he missed school to study the principles of interaction between electricity and magnetism, his teacher reprimanded him for showing disrespect toward the school's rules. Albert's parents found themselves torn between two choices: forcing him to obey discipline or allowing him the freedom to pursue his passion. In the end, Pauline nodded in support of her son, believing that Albert's sparks of spirit needed to be protected. Aside from his studies, young Einstein quickly integrated into the community of Jewish students in Zurich. There he met peers interested in modern politics and philosophy, discussing the first Soviet state, the doctrine of historical materialism, and even the earliest lectures on Darwin and evolution. On weekend evenings, they would gather around the apple tree at the school gate, engaging in fiery debates about individual liberty and the meaning of social uprising. Albert listened more than he spoke, but when he did speak up, he always presented sharp arguments grounded in physical formulas or empirical evidence he had gathered from books. Thanks to the encouragement of Professor Gresser and his close friends, Einstein began recording his thoughts in the form of a scientific journal. He labelled the entries in alphabetical order: A, on the nature of light; B, on the relationship between time and motion; C, on the structure of three-dimensional space. The journal pages were filled with bold handwriting, sometimes even including space-time diagrams to illustrate the interplay between the two concepts. Each evening, by the light of the oil lamp, and accompanied by the gentle piano music from the next house, Albert diligently recorded his first discoveries. Though the diagrams were still tangled, the grand ideas that would change the world were already forming in his mind. And then, on those windy Zurich afternoons, amid the simple tolling of church bells and the damp cobblestone streets, Albert Einstein clearly sensed that the path of science was not only the conquest of formulas, but also a journey back to the essence of truth. From the shy boy in Ulm, Albert had now become an eager student, ready to face every challenge, confidently stepping forward. And with each step, however slow, he was leaving an indelible mark. In 1896, just after his 17th birthday, Albert Einstein left the Zurich Cantonal School and officially enrolled at the Swiss Federal Polytechnic, ETH Zurich, where his research dreams would be both nurtured and rigorously tested. The spacious campus along the banks of the Limmat River, the red-tiled corridors, and the laboratories glittering with glassware welcomed Albert with a mixture of excitement and awe. For him, every lecture by Heinrich Friedrich Weber on electrodynamics or by Hermann Minkowski on the geometry of space felt like doors opening onto new horizons. From his very first semester, Einstein proved himself not one to be bound by convention. While his classmates adhered strictly to the prescribed study schedule, Albert often skipped certain basic theory classes to go straight to the library and read works such as Ernst Mach's The Principles of Mechanics or Sir Isaac Newton's treatises. He even secretly enlisted his steadfast friend Marcel Grossmann, a meticulous veteran of the programme, to share detailed notes from the official lectures, filling in the gaps he had missed in class. Einstein's reputation spread quickly among his close circle of friends, not only because of his outstanding academic performance, but also due to his talent for theoretical dialogue. He could debate the nature of light with Professor Hurwitz one day, then present a simple model explaining the photoelectric effect in the next session. In his adolescence, Albert formed a deep friendship with Mileva Maric, the first female student from Serbia, admitted to the Department of Mathematics and Physics at ETH. They exchanged problem sets, hummed through the formulas of partial derivatives, and even staged emotional experiments to test the interaction between two inquisitive minds. Nevertheless, Einstein's path at the Polytechnic was not without its obstacles. His relationship with Professor Weber was occasionally strained. Weber was displeased when Albert failed to follow the standard lectures and frequently skipped mandatory laboratory sessions. On one occasion, when Einstein missed a fluid mechanics lab because he was engrossed in reading Lagrange, Professor Weber reprimanded him in writing, "A lack of academic discipline will ruin your career." Yet in his heart, Hermann Weber could not deny the unique talent of his student. At the end of his third year, to complete the graduation requirements, Albert had to defend a short thesis on capillary action. This topic originated from the French edition of Les lois de l'attraction capillaire, which he happened to borrow from the Cantonal Library. In the ETH laboratory, by the light of an oil lamp and the hiss of water on the glass tubing, Einstein measured the wettability of glass surfaces, observed the height of water columns in capillary tubes of various diameters, and recorded every fluctuation, no matter how slight. The thesis manuscript, about 20 pages long, demonstrated both mathematical finesse and experimental meticulousness. When he submitted it to the examination committee, Albert merely smiled and said, "I hope it can contribute a little to the physics of fluids." In July 1900, the ETH Zurich commencement ceremony took place under a radiant sun. Albert Einstein, dressed in a simple gown, received his diploma as a physics engineer. With a commendation for excellence in mathematics and physics, Mileva Maric, standing beside him, gently tapped his shoulder and whispered, "We did it." Amid the thunderous applause, Albert lifted his eyes to the blue sky, envisioning the theory of relativity that would turn his ideas into reality, linking space and time in a way no one had ever imagined. But the joy of the commencement quickly gave way to anxiety as Albert began searching for a teaching or assistant position. Despite his excellent transcript, he was rejected by many universities for lack of teaching experience. 12 letters applying for lecturer, assistant, and research positions sent throughout Europe all received terse replies. His fiancée Mileva comforted him. "Our journey of discovery has only just begun." Undiscouraged, Einstein persisted in sending his dossier to the Swiss Federal Patent Office in Bern. There they needed a technical expert to evaluate patent applications for electrical devices, a job seemingly far removed from theoretical physics, but perfect for Albert to continue his research in his spare time. The job offer arrived in June 1902, marking the beginning of his legendary Bern years, where during breaks Albert and his friends would discuss light, motion and, at its pinnacle, the year 1905, his annus mirabilis, with 4 papers that shook the world of physics. And so, from the perfect circles drawn in childhood, from the capillarity experiments of his student days, Albert Einstein stepped into a new phase. Not a university lecture hall, but a patent office, where the free mind of a genius would shine more brightly than ever. In the summer morning of 1902, as Albert Einstein stepped through the gates of the Swiss Federal Patent Office in Bern, he carried with him a small suitcase of simple clothes, a thick satchel of books on electromagnetism, and grand dreams not yet fully formed. The grey stone building rose before him on the tranquil Kornhausplatz, where horse-drawn carriages clattered over cobblestones and the Münster church bells tolled in the hush. Each morning Albert walked along Niedergasse beneath the shade of an ancient linden tree, pausing to admire the old wooden Kramgasse bridge spanning the clear, murmuring Aare River, a reminder that time, though it flows gently, never ceases to move forward. Inside the patent office, Einstein's work seemed monotonous, yet perfectly suited to his exploratory spirit. His main task was to receive and evaluate patent applications for electrical devices, measuring instruments, and signal transmission methods. On his desk lay stacks of inventors' filings, alongside his personal notebooks, where Albert recorded ideas, formulas, and his observations about light and motion. Reviewing the schematics of a new generator, he assessed not only its technical feasibility, but also conceived how electromagnetic waves might interact with the surrounding space. After hours, instead of returning directly to his apartment on Schützengraben, Albert often strolled along the Are's banks, carrying Lord Kelvin's treatise on thermodynamics. Beneath the horse-chestnut canopy, sunlight danced across the pages, and birdsong mingled with the river's cool breeze. In those quiet moments, Einstein penned the equation that would later underpin the principle of relativity, that two inertial reference frames can each be regarded as at rest if distance and time are measured appropriately. In Bern, Albert found two kindred spirits, Maurice Solovin, a Romanian philosophy student, and Konrad Habicht, a Swiss mathematician. They met regularly at number 4 Kramgasse, home to a cosy corner cafe, fragrant with coffee brewed from golden roasted beans. On their wooden table lay open copies of Mach, Hume, and Boltzmann. There they debated the nature of light, particle, photon, or wave, Maxwellian. The earliest ideas of the photoelectric effect were kindled in these long discussions, when Albert posed that if light were merely a wave, how could it eject electrons from metal with energy dependent on frequency rather than intensity? By late 1903, Albert had completed his doctoral dissertation at the University of Zurich on heat distribution in gases, a concise work demonstrating a unified vision of classical mechanics and statistical theory. The 70-page manuscript was sent to Professor Alfred Kleiner, who graciously awarded him an honorary doctorate. In the dedication letter, Albert wrote, "I hope this small work contributes to clarifying the relationship between thermal energy and the random motion of molecules." Though readership was limited, it marked the first time Einstein's name appeared in a scientific publication. A few months later, in their favourite cafe, Albert read aloud to Solovin and Habicht the draft of On a Heuristic Viewpoint Concerning the Generation and Transformation of Light. Under the warm glow of oil lamps, his voice brimmed with excitement as he described the concept of energy quanta, each photon carrying energy proportional to light's frequency, E equal hn, as a solution to experiments that wave theory alone could not explain. When he finished, Morris asked, "Will they accept such a proposal, one that completely overturns Maxwell's wave model?" Albert smiled. "We shall see. In the end, experiment will decide." In 1904, amid Bern's springtime charm, Einstein submitted On the Motion of Particles Suspended in Fluids at Rest, a study of Brownian motion applying statistical theory to prove the existence of atoms and molecules. His careful calculations, experimental data borrowed from Perrin, and astute observations of random fluctuations convinced the European scientific community of the molecular model's validity. Several minor journals published the paper, and Einstein's name began to circulate, if softly. Then, on a summer evening in Bern in 1905, as the Münster bells tolled at dusk, Albert completed his final manuscript, On the Electrodynamics of Moving Bodies, centered on two pillars, redefining simultaneity between events and postulating that light travels in a vacuum at constant speed c. This paper would fundamentally change humanity's view of space and time. Once printed, Albert immediately sent it to Annalen der Physik with a brief note. To the editorial board, please consider the attached work. I believe it may be the beginning of a relativity theory that humanity seeks. That night, by the window overlooking the silent Aare, Albert sank into an armchair. On the table lay the three completed miracle papers: photoelectric effect, Brownian motion, and relativity. In his mind, he thought not of fame or future Nobel Prizes, but only knew that free thought and perseverance had brought him to the threshold of a new era. The water's gentle lapping seemed to whisper encouragement. Continue to explore. Continue to question. From those meticulous days at his desk in Bern, between cafe discussions and riverside strolls, Albert Einstein laid the foundations of special relativity, paving the way for the next chapter of his life, where modern science would transcend dreams to become an enduring legacy. When the last winter winds of 1905 swept through the city of Bern, Albert Einstein stepped onto a new turning point in both his scientific career and personal life. The three miracle papers had made a tremendous impact in European physics. The photoelectric effect introduced the concept of the photon, Brownian motion confirmed the reality of molecules, and special relativity redefined our notions of space and time. Although he was still working at the patent office, Einstein began receiving invitations to contribute articles to prestigious journals and to participate in academic conferences by correspondence, appearing for the first time on Annalen der Physik's list of researchers to watch. In mid-February 1906, the University of Zurich awarded Einstein the title of Privatdozent, unsalaried lecturer, in the Department of Theoretical Physics. The short train ride back to Zurich, where only 6 years earlier he had been an inexperienced student, awakened both memories and the opportunity for official teaching. In a small classroom on Ramestrasse, Albert stood before the blackboard, chalk in hand, conveying the principles of special relativity to eager students. Though his voice was still soft, and his lecturing style sometimes disorganised, the clarity of his explanations allowed his pupils to quickly grasp the groundbreaking ideas of simultaneity and the Lorentz transformations. Einstein's married life also began shortly thereafter. In June 1906, he held a simple wedding with Mileva Maric, his fellow student and close confidant who had accompanied him through so many days of research. The ceremony, attended only by family and a few close friends in Zurich, took place in their modest apartment on Kramgasse, which became the home where two journeys, scientific and romantic, would unfold. Mileva, herself well versed in mathematics and physics, continued to support Albert by proofreading his manuscripts and discussing concepts, even as she set aside her own studies to care for their family. However, the position of Privatdozent did not guarantee financial stability, so after a year of teaching, Einstein decided to return to Bern to keep his post at the patent office, while also accepting a part-time lecturing contract at the University of Bern. He and Mileva moved into a small apartment on Wiesenstrasse, furnished simply with wooden furniture, a few English and German language books, and a writing desk always strewn with sticky notes. Their first son, Hans Albert, was born in May 1904, like a burst of laughter amid life's demands. And just when the family needed every franc, Mileva grew increasingly occupied with childcare and began accepting translation work for Annalen der Physik. On the research front, Einstein set to work extending relativity. He spent evenings studying how gravity operates and how it might affect the flow of time. His earliest entries in the Gravitational Notes notebook remain rudimentary, pencil sketches of curved space, tensor symbols flickering across blank pages. In the autumn of 1907, while experimenting to measure freefall acceleration in weak gravitational fields, a sudden insight struck. A person in a freely falling elevator would not feel their own weight. That seemingly simple question became the seed for the general theory of relativity, opening the dramatic next chapter of Albert Einstein's genius journey. In the final months of 1907 and the early months of 1908, the idea that a person in a freely falling elevator would not feel gravity became increasingly clear in Einstein's mind. He diligently wrote in his notebook, drawing curves representing the trajectories of objects in a gravitational field, and tried to compare them with uniform motion in flat space-time as in special relativity. Every night when the oil lamp in the Wiesenstrasse living room dimmed, Albert would sit tapping on the window pane, his eyes fixed on the silent space outside, as if seeking there the image of the curved space he longed for. The road to the University of Prague. In April 1910, after years of preliminary work, Einstein accepted an invitation to become professor of theoretical physics at the German University in Prague, now the Czech Republic. This was a major transition, from Bern's patent office to an official university lecture hall where he could freely research and express his ideas. Mileva and Hans Albert accompanied him to Prague. The little house on Karlova Street became their new home. With his violin providing accompaniment for his writing nights, Albert began giving fresh lectures on special relativity to Czech and German students, drawing curves of space. In Prague, Einstein spent most of his time in the Strahov Library, borrowing Poisson's Celestial Mechanics and Richie Cartan's Introduction to Tensor Analysis. He sketched diagrams illustrating how a freely falling object in a gravitational field moves equivalently to straight-line motion in a falling reference frame. From this, he formulated the equivalence principle. An observer in a sealed cabin cannot distinguish between a gravitational field and the acceleration of the reference frame. First astronomical calculation. In April 1911, Einstein moved to a special professorship at ETH Zurich and submitted his first paper applying the equivalence principle to an actual observation. Starlight passing near the sun would be slightly deflected by its gravitational field. He estimated the deflection angle at about 0.83 arc seconds, roughly half the value later confirmed. Although the figure was not yet precise, the paper asserted that general relativity was no longer a purely geometrical story, but could be tested astronomically. Exchanges with European scientists. Throughout the summer of 1911, Einstein travelled extensively, from Zurich to Leiden to meet Hendrik Lorentz, who had supported the Lorentz transformations, then to Brussels for the International Science Congress, where he presented the concept of curved space-time to both admiration and skepticism. In Berlin, Planck invited him to the Max Planck Institute for a deeper discussion on the link between thermodynamics and gravitation. These interactions not only broadened Einstein's perspective, but also helped him refine his mathematical language, especially through collaboration with his old Zurich friend Marcel Grossmann, an expert in tensors and Ricci calculus. Criticism and refinement. Despite his enthusiasm, Einstein faced considerable criticism. Colleagues argued that general relativity demanded overly complex calculations, difficult to verify experimentally. His perseverance kept him going. He exchanged letters with David Hilbert, one of the era's greatest mathematicians, inviting him to reconsider the gravitational field equations. After many revisions, the two independently arrived at a unified form now known as the Einstein field equations. G mu nu plus lambda G mu nu equals 8 pi G over C to the fourth times T mu nu, expectations and preparation for the 1914 eclipse. By late 1912, with the framework of general relativity nearly complete but lacking empirical field tests, Einstein returned to Germany as a professor at the University of Berlin. He and Freundlich, along with other German colleagues, planned to use the total solar eclipse of 1914 to measure starlight deflection, an essential test of his theory. All of Einstein's new notes and estimates were compiled in his black logbook, from the curvature of space around the sun's mass to the telescope's lens properties. Thus, 6 years after leaving Bern, with his 3 miracle papers, Albert Einstein stood on the threshold of the gravitational era. General relativity, with its wondrous tensor calculus and immortal equivalence principle, ready to be tested against the real sky. The road ahead was fraught with challenges, but also sparkling with promise, awaiting Einstein as he led humanity into a new horizon of understanding the universe. When the door of 1914 closed in Prague, Albert Einstein left the misty city to set foot in splendid Berlin, a centre of science, art, and politics transforming under the influence of the looming First World War. Having accepted the professorship at the University of Berlin, and at the same time a seat as a member of the Prussian Academy of Sciences, Einstein moved with Mileva and their 2 children into a luxurious apartment on Unter den Linden, beside the grand boulevard leading straight to the Brandenburg Gate. Beneath the April sunshine, the ancient oaks cast cool shade over the walkways lined with stone benches for passers-by, and the bells of the Friedrichswerder church echoed through the neoclassical columns. Once settled, Einstein found the atmosphere in Berlin entirely different from Bern or Zurich. He frequently invited friends, colleagues, and even statesmen to discussions, ranging from Max Planck and Rudolf Ladenburg to Philipp Leonard, in his tidy salon, where an oil painting of the Göttingen landscape hung on the wall. On the coffee table lay a neat stack of books: Planck's Quantum Physics, Lorentz's Lectures on Electrodynamics, and the manuscript Einstein long referred to as his Red Notebook, in which he recorded the final calculations for the gravitational field equations. The scent of Earl Grey tea wafted through the room, and the gentle strains of violin from his young friend Lisa Meitner filled the air, creating an atmosphere both intellectual and intimate, perfecting the field equations. In his early months in Berlin, Einstein spent most of his time in his office at the Academy on Wilhelmstrasse. By the warm glow of sodium lamps, he sat with pile upon pile of tensor notebooks, redrawing each Ricci component and continually revising his initial equations. Day after day, scrap papers covered his desk, the symbols G mu nu, R mu nu, and T mu nu danced across the pages like the skeleton of a new theory. With the support of Marcel Grossmann, who had given Einstein a copy of Tensor Analysis by Ricci and Levi-Civita, by late 1915 he officially completed the Einstein field equations in the form G mu nu equals 8πg over c to the 4th times T mu nu. From that point on, gravity was no longer a mysterious, guiding star, but arose from the curvature of space-time caused by matter and energy. Publishing General Relativity, on November 25, 1915, at the final meeting of the Berlin Academy's physics section, Einstein presented the full structure of the general theory of relativity. The audience, jotting notes furiously, displayed a mixture of admiration and skepticism. 2 weeks later, 4 papers collectively titled The Gravitational Field Equations appeared in Annalen der Physik, marking the first widespread publication of the new theory. As Berlin edged ever closer to war, news from France, England and America had yet to arrive. But Einstein's name was already echoing throughout Europe, preparing for the eclipse test. Alongside finalising his theory, Einstein did not neglect experimental verification. He reached out to Arthur Eddington in England and Erwin Freundlich in Germany to observe the total solar eclipse of 1919. He enclosed in his correspondence the sophisticated calculation for the deflection angle of starlight grazing the sun. Delta theta equals 4gm over c squared b, where bb is the closest approach of the light ray to the sun's centre. Though the war disrupted many resources, Einstein persevered in keeping contact with colleagues across Europe. Life amidst war. By early 1916, when war broke out, Berlin suffered shortages of fuel and food. Einstein and his family adopted a frugal diet. His son Hans Albert went to live with Mileva's parents in Zurich until the conflict eased. In response to the urgent situation, Einstein joined the anti-war movement, publicly signing the Gettysburg Declaration, calling for an end to violence and a diplomatic solution. His courage earned him the scorn of many militarist colleagues, but also the support of peace-loving intellectuals. A vision beyond hardship. Despite Berlin's bleakness, scarred by artillery fire and growing hardship, Einstein stayed true to writing his book, The Theory of General Relativity and Its Applications, scheduled for publication in 1918. Nearly 300 pages long, the volume presented not only the principles and equations, but also practical applications, from gravitational redshift to time dilation at the mouth of a volcano. While other European cities burned, Einstein wrote undisturbed, confident that science would transcend all borders. Thus, amid the smoke and fire of war, Albert Einstein stood not only as a physicist, but as a symbol of hope and human intellect. Guns might extinguish the oil lamp, but they could not dim the pen he wielded across blank pages, where numbers and tensor symbols continued to sketch a new world, in which space and time dance together in the waltz of gravitation. The story brings us back to the skies of May 1919, when English astronomers travelled to Príncipe Island off the coast of West Africa, and their colleagues to Sobral, Brazil, to witness the total solar eclipse. News of the scientific mission swept across Europe, the promise of testing one of the boldest predictions of general relativity. In his quiet Berlin study, Albert Einstein followed every step of the preparations by correspondence with Arthur Eddington and Frank Dyson, each letter heavy with hope and anxieties over wartime shortages of supplies. As the sun's disk was gradually obscured, the scientific world watched anxiously through telescopes. The Earth slipped into momentary darkness, and stars normally visible only at night suddenly appeared just beside the sun's rim. On the photographic plates, the tracks of starlight curved gently around the bright solar limb. Under damp skies and a chill sea breeze, Eddington surveyed the initial measurements and smiled. The deflection angles matched Einstein's prediction more closely than any other theory. News spread swiftly from Sobral to Cambridge, and then across the Atlantic to Berlin. Einstein received the telegram with his heart racing. The data confirmed that starlight truly bent when passing through the sun's gravitational field, exactly as he had foretold via the field equations. Amid wartime Berlin, this announcement brought pride and new hope for international scientific collaboration. In late summer, during a meeting at the Academy, Einstein embraced Eddington over the telephone line. "We have touched it." The fame of general relativity quickly leapt beyond academia. London, Paris, and New York newspapers ran Einstein's likeness, his wild hair and kindly eyes, alongside commentary proclaiming that science had found a new star. In Berlin, people competed to buy science journals to learn about the light-bending effect, and students queued to register for his lectures. His talks at the University of Berlin filled every seat. Many were forced to stand in the corridors, listening through half-open doors. Sudden celebrity did not change Einstein. He stuck to his routine of rising early and jogging around Lake Wannsee before heading to the lecture hall. His desk remained strewn with sticky notes of formulas and symbols, annotations on how to extend relativity toward cosmology. Mileva, though separated from him, kept in touch by letter and often sent photos of their son, Hans Albert, with well wishes. Einstein spent spare hours reading Dante's Divine Comedy and Schopenhauer, seeking inspiration from literature for the next twists in his research. In post-war Germany, the new government was preoccupied with rebuilding society, but could not ignore the influence of this great scientist. Einstein was invited to advise the Ministry of Education and Information, urging investment in engineering education and physical research. He refused to enter politics directly, but argued that science must remain independent and serve humanity. His short speeches were later collected in Science and Peace, published and circulated across Europe as a voice turned toward the future. Despite his widespread acclaim, Einstein remained focused on fundamental questions. the nature of the cosmological constant, the possibility of gravitational waves, and the practical implications of relativity for spacecraft technology. He spent the winter of 1920 investigating models of cosmic expansion proposed by Alexander Friedmann and Georges Lemaitre. His notebook pages reveal undiminished enthusiasm. Every number, every tensor symbol still sparked wonder and curiosity. Then, on a spring morning in 1921, as news of his new research projects spread, Einstein received the Nobel Prize in Physics for his work on the photoelectric effect, rather than for general relativity. The decision provoked controversy, but underscored the importance of the photon concept. On the Stockholm stage, he quietly accepted the gold medal, smiling at the sea of cameras and uninterrupted applause. Yet in his private thoughts, Einstein longed for people to delve deeper into curved space-time and the matter-energy connection, not stop at light as particles. From Bern to Berlin, from Princeton to the Nobel podium, Albert Einstein's journey demonstrates the power of free thought and faith in experiment. Every step led to a new question. Every discovery opened another horizon. In the realm of science, he etched his name not only with numbers and tensor symbols, but with a legacy of perseverance, humility, and an unwavering pursuit of truth. And the story of the man who bent light continues, guiding humanity ever deeper into the universe's mysteries. The autumn of 1921 brought Albert Einstein not only the crisp winds of Berlin, but also a transatlantic journey, an invitation to lecture on relativity in the United States, and to receive his Nobel Prize in Stockholm, making him a distinguished guest in lecture halls and scientific forums across the country. As the train slowly carried Einstein and his son, Hans Albert, to the port of Cherbourg, the vast blue ocean spread out before him like an endless map, reminding him of the formulas and tensor symbols still suspended in his thoughts. The steamship crossed the ocean over 12 days, its elevators jolting with each high wave. In the small cabin, Einstein never left his notebook. He recorded ideas about gravitational waves and the consistency of the field equations when applied to the distant universe. When mist first obscured New York's harbour, Albert felt keenly the desire to explore vast spaces, not only the cosmos, but also his own place amid new civilizations. Now that prestigious American universities, Princeton, Harvard, and Caltech, awaited Einstein with hundreds of students packed into their lecture halls. Each lecture painted a vivid picture of curved space, light bending around massive bodies, and a call to trust in experiment. His voice rang out in the auditorium, no longer the halting German-English mix, but an invitation to a generation of young scientists to continue the quest for truth. American students, accustomed to practical engineering instruction, for the first time felt the romance and freedom of theoretical science. Outside the classroom, Einstein visited the Smithsonian in Washington, conversing with Thomas Edison and Robert Millikan about applications of relativity in electrical technology, though he always insisted that basic science remained the foundation of innovation. At the Rockefeller Center, he delivered an address urging international cooperation in research, calling on the United States to expand funding for pure mathematics and physics. His remarks about our shared human space and respecting knowledge across borders gave many politicians and donors much to reflect on. The 6-week tour concluded with a grand farewell banquet in New York City. In that solemn atmosphere, Einstein received a letter from the Berlin Academy announcing that his field equations had passed every initial experimental test and had become one of the cornerstones of modern physics. Holding the letter, he felt a quiet pride, not for the acclaim itself, but because day by day, the numbers and tensor symbols he had written were lifting the veil on the universe's mysteries. Back in Europe, Einstein had no time to rest. The English edition of his book, The Theory of General Relativity, and its applications was about to appear, and he focused on writing a new chapter on cosmology, the idea of an expanding universe drawn from the work of Friedmann and Lemaitre. he sketched the first illustrations of a dynamic universe, rather than a static one, and debated with colleagues the cosmological constant L, whether it was a mere fudge factor or revealed the deep nature of space-time. Amid his research, his marriage to Mileva finally unravelled. Their letters grew shorter, filled with worries about Hans Albert's future, but leaving little room for their shared scientific passion. Einstein moved to a smaller apartment on Haberland Street, where he lived chiefly with his assistant Helen Ducasse, the loyal guardian of his household and caretaker of all his important manuscripts. The friendship between Helen and Einstein, together with a distant but respectful connection to Mileva, came to define his new life, where science and inner peace walked hand in hand. From 1923 to 1925, Einstein continued his quest for a unified theory of electromagnetism and gravitation, but had not yet found a mathematical language powerful enough. His black notebook pages filled with formulas, yet experimental tests remained beyond his reach. Still, every time he published a small paper, he received feedback from Max Born, Niels Bohr, and Erwin Schrödinger, the rising stars of quantum physics. Though he never fully embraced Heisenberg's uncertainty principle, he encouraged his colleagues to explore it, believing that the future of science lay at the intersection of the two theories. One spring morning in 1926, amidst birdsong on his porch and pale sunlight through the trees, Einstein returned to the Sonnenwarte Observatory in Potsdam to meet astronomer Erwin Finley Freundlich. They discussed a new plan to search for gravitational waves using microwave telescopes, hoping that a decade later, technology would be sensitive enough to detect space-time's subtle ripples. Of course, at that time science could not yet prove it, but Einstein's curiosity still burned fiercely. Thus, this third chapter closes not with a final sentence, but with the silent chord of aspiration, the aspiration to conquer the vast universe through theory and experiment, to sow hope for peace and global cooperation through the language of science, and above all, the aspiration to remain bound for life to the numbers and tensor symbols that continued to dance in Albert Einstein's mind. When the first spring rays of 1927 filtered through the window of his office at the Prussian Academy of Sciences in Berlin, Albert Einstein smiled softly as he gazed at his cosmology notes. He had just completed a manuscript on an expanding universe model in which the cosmological constant L was not merely a memoryless constant, but could vary with the matter density. This insight built on calculations by Georges Lemaitre and Alexander Friedmann. But Einstein added corrective factors related to vacuum energy, paving the way for what would later be called dark energy. On the desk, his violin and its gentle case lay untouched, a bridge between science and art in his soul. In the silent room, only the ticking of the grandfather clock could be heard. With each tick, Einstein imagined feeling the vibrations of space-time itself, recalling the gravitational wave idea he had first proposed a decade earlier. He squinted at his sketches of proposed telescope monitoring sites, places where one day not far off, those faint ripples might be measured. Late that spring, Einstein accepted an invitation to teach and conduct research at the Institute for Advanced Study in Princeton. The tranquility of New Jersey was a world apart from Berlin's intensity. Dawn light shimmering on Carnegie Lake, pigeons cooing on stone benches. There he joined the theoretical physics community led by Niels Bohr, Werner Heisenberg, and Paul Dirac. Though he never fully embraced the uncertainty principle, Einstein took part in quantum mechanics seminars, famously declaring, "God does not play dice with the universe." His words quickly became emblematic of his conviction that every physical phenomenon must ultimately be determinate, though the core debate remained about the nature of probability itself. Between heated debates, Einstein corresponded widely with astronomers around the globe. He exchanged letters with Edwin Hubble about galactic redshifts, absorbing the latest distance measurements from Mount Wilson Observatory. From these figures, spanning millions of light years, Einstein noted his excitement. The universe not only expands uniformly, but may accelerate, raising the question of what mysterious push drives this effect. His scrawled margins seemed to dance to the rhythm of the coffee cup's tremor on his desk. At Princeton, Einstein also threw himself into peace and human rights causes. He signed manifestos against nuclear weapons and published articles in European journals urging atomic technology controls. He spent long evenings discussing with his wife Elsa how science could serve peace. Elsa listened in quiet support, hosting warm dinners that helped him balance intellectual strain with inner calm. Through the late 1920s, Albert wrote a comprehensive monograph on general relativity, adding new chapters on cosmology and gravitational waves. He diligently typed drafts, often rewriting sentences to ensure the prose remained non-dogmatic, yet mathematically precise. In the afternoons, he strolled through the campus gardens with Helen Dukas, pondering how to explain space-time curvature in terms accessible to every reader. One autumn evening in 1930, under the dim glow of his lamp, Einstein read in the New York Times about the newly discovered neutron stars and black holes, objects barely explainable by classical mechanics. He smiled, thinking that the universe always finds surprises to challenge every theory. He sighed and jotted in his notebook, "We have far more questions than answers." From that moment, Einstein's focus shifted to unifying general relativity with quantum physics, embarking on the quest for a true theory of everything. When the first spring rays of 1931 filtered through the window of his office at the Prussian Academy of Sciences in Berlin, Albert Einstein smiled faintly at the manuscript before him, titled Unsolved Problems of General Relativity. The bold lines on the white pages seemed to echo the murmurs of the universe, urging him to find a way to unite gravitation with electromagnetism and quantum physics. Beside the typewriter, a cup of coffee sat cooling, proof of his unceasing passion. In the mornings, he typically began with a walk along the Forbes Trail, where rows of oak trees leaned their shadows across the gravel path. The breeze carried moisture from Carnegie Lake. And in that stillness, Einstein listened for the heartbeat of ideas. If the cosmological constant L truly represented vacuum energy, then it might vary with the changing fabric of space-time, creating a strange, repulsive force that pushes galaxies ever farther apart. This notion alone could open an entirely new direction in cosmology. Back in his study, he spent hours corresponding with Georges Lemaitre, then working at the Vatican Observatory. Though their tongues differed, they shared a common yearning to uncover the universe's primordial origin, from the moment of the Big Bang to when the cosmos cooled enough for light to be liberated from its primordial furnace. That exchange gave Einstein the sense that science knows no borders, but serves as a bridge connecting souls across vast distances and beliefs. Midweek at lunchtime, he would stop by Princeton's Firestone Library to read the latest papers on non-relativistic quantum mechanics. Heisenberg's and Schrödinger's articles still puzzled him. How could one reconcile the random probabilities of the quantum world with the absolute determinism he held dear? He sketched dots and arrows on scrap paper to represent probability amplitudes, then wondered, might there exist some hidden matrix governing all quantum outcomes by a yet undiscovered law? Though the idea of an hidden variable remained vague, it thrilled him enough to keep scribbling. In the late afternoon, Einstein invited Helen Dukas and his French friend Bernard Fay to his small house on Mercer Street. Over warming tea served with pumpkin cake and apple pie, laughter filled the room as Helen recounted family anecdotes, while Bernard shared the latest political observations from Europe, rising nationalism and the threat of new conflicts. Einstein, ever a man of peace, listened intently and warned that if science did not promote a shared human vision, even the most elegant equations could not save the world from crisis. A few days later, he received a telegram from the Berlin Academy of Sciences announcing plans to commemorate the 10th anniversary of General Relativity's publication. Though busy, Einstein sent them an address in German, emphasizing, A scientific theory is only valuable if it helps humanity understand one another and live in harmony. Those simple yet profound words recalled the image of him, amid wars, smoke and fire, calling for ceasefires and the protection of science. One early summer evening, after dispatching his address, Einstein stepped into his backyard and looked up at the starry sky. Holding his notebook, he jotted a line. Space-time is a fabric woven from the substance of possibilities, and only when we draw new curves upon it does the universe reveal itself. The golden light in his study window flickered in sympathy, witnessing that sacred moment where destiny and scientific thought converged. The political and social upheavals of the 1930s seemed to resonate powerfully with the complex field equations of Albert Einstein. When Hitler came to power in Germany, the brilliance that once illuminated Berlin faded into deep darkness. Einstein, an openly Jewish humanist and pacifist, became a target of Nazi attacks. The bad news arrived one winter morning in 1933, when he received a telegram from the Berlin Academy announcing that all his rights and positions there were suspended, the first step toward fully stripping him of his role. Without hesitation, Einstein and his assistant Helen Dukas packed their bags and left Berlin just weeks later. Their Mercer Street apartment in Princeton was ready to welcome him back to the United States as a place of safe refuge. On the steamship crossing the Atlantic, he gazed at the churning Black Sea under the rain, his heart stirred by memories of happier years, yet resolved that the freedom of thought in America would give him the space to continue his quest for a unified field theory, the dream he most wished to fulfill in his final years. Back in Princeton, Einstein was greeted by the warm embrace of colleagues and students. In Fuld Hall's library, with its large window overlooking the silent campus gardens, he resumed work on extending his theory of gravitation to include electromagnetic interactions. For months, Einstein tirelessly recorded equations transforming Maxwell's field into tensor components, hoping to discover a general form. Nabla nu f mu nu equals lambda g mu nu partial nu r, where f mu nu is the electromagnetic tensor, r the scalar curvature, and Lyell an adjustable constant. Each stroke of his pen and every line of formula expressed his longing to find a formula of everything. Amid these intense research hours, Einstein still devoted time to democratic and human rights causes. He signed declarations opposing fascism, spoke out strongly against nuclear weapons programs, and urged the US government to support European political refugees. His letters to President Roosevelt, while warning of Germany's potential to develop an atomic bomb, also conveyed deep respect for the creative spirit of science, showing that his objection was not to nuclear research per se, but to its disastrous misuse by inhumane regimes. Einstein's unified field research spanned the decade, yet he repeatedly encountered obstacles. The mathematics of modern gauge fields, like Yang-Mills, had not yet been developed, and the concept of quantum fields remained incomplete. Nevertheless, he persevered. In 1935, together with mathematician Leopold Infeld, Einstein published The Determinacy of Field Theory, attempting to construct a multi-component tensor model uniting electromagnetism and gravitation. Though the paper was not warmly received, it demonstrated his unflagging creativity and tenacity. By mid-1939, as the Second World War erupted, Einstein recognized that nuclear science had become a double-edged sword. He and many fellow scientists wrote letters calling for a halt to destructive weapons research, established the Einstein Fund to support Jewish scientists fleeing fascism, and energetically gave fundraising lectures for the United Nations after the war. In addition to speaking before the San Francisco General Assembly in 1945, he published political commentaries, such as Science and the Common Good, to spread his message. In his final years, despite declining health, Einstein's mind remained sharp. He continued exchanging letters with Wolfgang Pauli, Erwin Schrödinger, and Nathan Rosen about nihilistic field equations, and critiqued the uncertainty principle. I do not believe that the universe tolerates ambiguity. Yet it was precisely these debates that propelled theoretical physics forward in mid-20th century science. By the autumn of 1955 in Princeton, Einstein would often settle into his familiar armchair in the study, surrounded by thousands of pages of incomplete manuscripts. One misty morning, he suffered a sudden heart attack and passed away peacefully, leaving behind an immense legacy. A complete theory of relativity, dozens of seminal papers, and enduring contributions to human rights, peace, and the collective knowledge of humanity. Albert Einstein may have departed, but the man who bent light lives on in every curve of space-time, in each atom and cosmos-shaping discovery, and above all, in the relentless journey of a humanitarian genius. The gentle spring dawn of 1956 spread across the grounds of the Institute for Advanced Study in Princeton, where the stone steps still bowed to welcome the morning mist. Albert Einstein's legacy lived on vividly. In the laboratory bearing his name, the Einstein Fellowships, and the meticulously preserved notebooks in Firestone Library. Whenever students and faculty passed the door of his former office, they felt the breath of a new scientific era he had inaugurated. Research groups applied general relativity to chart Pluto's orbit and map the Milky Way's gravitational field. Astronomers used the Einstein de Sitter equations to simulate the universe's expansion rate, while particle physicists pursued a unified field theory, striving to link the weak and strong forces in the way Einstein once dreamed. Annual Einstein Legacy Symposia became forums for reporting on gravitational waves, black holes, and cosmic wormholes. On the societal front, the Einstein Fund continued to support refugee scholars seeking freedom in the Americas and Europe. Scholar exchange programs between Princeton and the Hebrew University of Jerusalem fostered east-west and north-south connections, embodying the borderless scholarship Einstein championed. Each in memory of Albert Einstein Fellowship ticketed its recipient not only into classrooms, but also served as a reminder of intellectual freedom and humanitarian spirit. Years later, as the first radio telescope rose at Arecibo and the Hubble Space Telescope soared into orbit, general relativity once again proved its enduring worth. Light from distant stars bent around the gravity of ancient galaxies, creating Einstein rings, optical halos visible only through the curvature of space-time. Those images enchanted astronomers and confirmed Einstein's mathematical prophecy to a precision of 1 part in 1,000. Meanwhile, in education, a series of children's and young adult books titled Adventures in Spacetime with Albert introduced readers worldwide to simultaneity, four-dimensional spacetime, and relativity through lively cartoons and illustrations. From Tokyo to Sao Paulo, teachers explain the equivalence principle with model elevators crafted by students, showing a new generation that relativity bridges mathematics and wonder. Amid these achievements, a monument was unveiled in Ulm, the city where Einstein was born. It depicted him seated, drawing perfect circles with a compass, with dancing numerals behind him, spelling out E, Ul's MC2. Thousands attended the ceremony, bringing books, flowers, and letters of gratitude. Little children, eyes wide, gazed up and wondered, will I one day draw the universe's secrets? Meanwhile in Geneva, UNESCO established the Einstein Prize, honouring individuals and organisations for outstanding contributions to science and peace. The medal bearing his name symbolised not only academic achievement, but also the aspiration to build a world where knowledge underpins shared prosperity. Einstein's legacy extends far beyond discoveries in the distant cosmos. It permeates everyday life. The Global Positioning System, GPS, now indispensable in information technology and transportation, operates with pinpoint accuracy thanks to two relativistic effects: time dilation from the satellite's high orbital velocities and gravitational time delay due to the weaker gravitational field at altitude. Today's engineers and scientists, when calibrating atomic clock frequencies, still reference the formula delta T equals T0 square root of 1 minus V squared over C squared. a clear demonstration that both special and general relativity not only exist on paper, but guide modern life. Meanwhile, the 21st century has witnessed a breakthrough in gravitational waves. In 2010, LIGO in the US, detectors finally recorded space-time ripples produced by the merger of two black holes. The characteristic chirp signal on the control screens prompted physicists worldwide to pay tribute to Einstein. He had predicted that space-time could oscillate like a pond surface when struck by a stone. Italy's Virgo Observatory then joined the effort, inaugurating the era of gravitational wave astronomy and allowing humanity to hear the universe through its own vibrations. Research into black holes also cements Einstein's pioneering role. His field equations enable calculation of the Schwarzschild radius, defining a black hole's event horizon. Hawking radiation calculations, even though Einstein never fully embraced quantum probability, illustrate how black holes might evaporate via quantum effects, a fusion of general relativity and quantum mechanics that he could only begin to imagine. In particle physics, CERN experiments are probing the Higgs boson's interaction with gravity, the first step toward a unified field theory. While the Standard Model has explained mass generation, Einstein's dream of a closed-form framework for all interactions remains unfulfilled. Yet each new data point, from proton and electron collisions, fuels fresh hypotheses, propelling forward the journey Einstein launched. On the philosophical and cultural plane, Einstein's image stands not only as a scientific icon, but also as a symbol of intellectual freedom. Quotes like, "Imagination is more important than knowledge," appear on t-shirts, backpacks and posters worldwide. Children from Mumbai to Reykjavik learn of him as a great teacher, seeing in his wild hair and gentle smile a model to dare to question, to ask why, and to dream of the unknown. Interactive science museum exhibits let visitors experience faster-than-light travel effects, or simulate time dilation under relativity, making Einstein a bridge between past and future, between austere mathematics and wondrous adventure. The autumn day in Princeton was tinged with golden hues as the last students of the Relativity theory course filed out of Fuld Hall. In the room where Albert Einstein once lectured, his portrait still hung proudly beside the blackboard, its chalk dust bearing the equation G mu nu equals 8 pi g over c to the 4th times t mu nu. Down the corridor, voices drifted through glass-panelled doors, explaining how GPS measures time dilation, and computer screens blinked with gravitational wave simulations. In the final days of fall, Dr. Maya Patel's research team from India presented their survey of Einstein rings, images of distant galaxies magnified into luminous arcs against the cosmic backdrop. Using data from the James Webb Space Telescope, they demonstrated that Einstein's theoretical framework still dissected the fabric of space-time with precision, even at distances of billions of light years. The hall erupted in applause at the sight of those fantastical colours and shimmering optical halos, like shards of glass recombined. At the same time, engineers at CERN announced a breakthrough in particle collision experiments, a faint signal hinting at the existence of the quantum graviton, an entity once thought to reside only in Einstein's imagination. All eyes scrutinized the tiny statistical deviations in the data, for if confirmed, this would be the final piece in the puzzle unifying the fundamental forces. In that moment, one could almost see Einstein's presence as a great tree, its shade encouraging the scientific community to persevere through decades of challenges. Around the world, artists and writers continue to draw inspiration from Einstein's image. A play at Berlin's National Theatre portrayed his life through whispered soliloquies on the freedom of science. A Japanese animated film told the story of the boy who drew circles, becoming a great scientist, inspiring children everywhere to sketch their dreams and reach for them. In Vietnam, universities held an Einstein Within Me competition, where students pitched startup projects combining artificial intelligence and astrophysics. Amid this multidisciplinary creative flow, Einstein's spirit, belief in open education, international cooperation, and science for humanity remained intact. Early this year, the Hebrew University of Jerusalem inaugurated a research centre bearing his name, where Jewish and Arab scientists work side by side, defying political tensions to place knowledge above all else. Together they launched a desert-based gravitational wave observatory in the Negev, installing one of the world's most sensitive detectors. In the spring of 1946, as the last warmth of winter melted away across Princeton's campus, Albert Einstein spent his early weekdays catching up on letters from friends around the globe. He had just turned 67, his hair silvered completely, yet his eyes still shone with research fervour and deep faith in humanity's future. Under the weeping willow before 112 Mercer Street, he and Helen Dukas strolled slowly, discussing the urgent issues of the day, healing a war-torn world, controlling nuclear arms, and building a common home for science and civilization. In mid-May, Einstein accepted an invitation to visit Palestine from the Hebrew University of Jerusalem's Board of Governors. This trip spoke to a long-held concern. He had always supported creating an advanced educational centre for Jewish scholars in their ancestral homeland. In Jerusalem's clear spring sky, over a land reborn after conflict, Einstein stood before the newly founded library and physics department, where ancient Greek star symbols still adorned the stone walls. He joined fellow academics and spoke with Professor Chaim Weizmann about attracting international students and preserving Hebrew in the science curriculum. He emphasised, "Science knows no borders, yet it must also safeguard culture and language, so that each civilization can give voice to its own heritage." Back in Princeton, Einstein threw himself into the Unified Field Project once more. Although measurement technologies of the day lacked the sensitivity to test his new formulations, he, Leopold Infeld, and Banesh Hoffman debated how to merge the electromagnetic and gravitational fields into a single general expression. Late afternoons found him at his study window, overlooking the garden, Physical Review open to its unified field theory section, as he transcribed every line of nabla lambda m mu nu rho sigma plus ... equals 0. In his mind's eye, Einstein still believed that one day humanity would reach the theory of everything. At the same time, he felt the responsibility of a scientist extended beyond discovery to preserving humanist values. Einstein signed treaties banning nuclear tests and wrote open letters to the United Nations proposing an independent scientific commission on nuclear issues. Every letter bore his bold signature. "I cannot remain silent when the power of science becomes a threat to life." His message to the UN Secretary-General stressed educating the public about the arms race, for only knowledge could steer humanity away from the madness of war. In 1948, amid sweeping political changes in the Middle East, Einstein was invited as an honorary member of Israel's National Council. Although he never took Israeli citizenship, he devoted time to advising on STEM and social science curricula. In a Haaretz interview, he confided, "I rejoice to see a nation rise from the ashes of war, yet I worry that internal conflicts may erode the power, spirit of science and international collaboration." One early autumn afternoon in 1949, Einstein received a letter from Robert Oppenheimer inviting him to join the Scientific Advisory Board for Project Vienna, a European consortium aiming to develop peaceful nuclear energy. Though wary of weaponization, Einstein agreed on condition that he serve only on the biomedical and civilian energy committees. He noted in his diary, "Nuclear energy, like Prometheus's fire bestowed on humankind, can bring light or destruction if we are not vigilant." And in those final days of the year, as dew glimmered on the maple leaves outside his window, Albert Einstein never set aside his pen. He spent his last hours drafting a letter to UNESCO, proposing the establishment of the Einstein Prize for Peace and Knowledge, to honour young scientists' contributions to education and sustainable development. In the flowing ink across those pages, one could still sense the warm spirit of a genius, ever focused not only on the cosmos but also on community, on the dreams and hopes of generations to come. In the early days of 1950, Princeton remained shrouded in a light mist, enveloping the campus's tranquil beauty. Einstein spent his mornings at the window of his study, sipping hot tea and rereading invitation letters from around the world, from the American Geophysical Union and the Indian Institute of Physics to the Soviet Academy of Sciences. Though advanced in years, he continued to consider participating in international conferences by correspondence or recording talks, for to him, geographic boundaries could never divide the pursuit of scientific truth. The final thesis manuscript he sent out was entitled The Hidden Relations of Unified Field Theory, in which he once again attempted to link curved space-time with quantum fields. On the draft pages still lingered faint pencil sketches hinting at multi-dimensional structures and unresolved spin quantities. He signed boldly at the bottom, A. Einstein, Spring at 82, a testament both humble and proud of his unceasing ambition. In April 1951, as warm sunlight filled the newly inaugurated Einstein Archives exhibition hall, he visited it alongside young scholars. In the entrance foyer, facsimiles of his diary pages and original formulas were displayed with reverence, drawing the gaze of successive generations of students. Einstein leaned on the railing, his eyes distant as he recalled the long journey, from the boy who drew circles to the calculations that changed humanity's understanding of the cosmos. That summer, his health occasionally faltered. A persistent cough once forced him to pause all work, but after a few days of rest beneath the willow's shade, he returned to his desk. His spirit was greater than his frail body. He spent afternoons writing to Bertrand Russell about the necessity of global nuclear disarmament and drafting a talk for the United Nations, despite having declined many long-distance invitations. In autumn 1952, Einstein received an offer from Israel's Secret Service, nominating him as honorary president of the newly established state. His polite reply declined the honour, citing his need to devote himself fully to research, yet it expressed deep affection for the Jewish people and a desire to contribute further to education and science. "I am not a politician," he wrote, "but I believe science can sow hope in the human spirit." The last letters he penned in early 1953 revealed his profound engagement with philosophical issues. He quoted Spinoza, affirming that the universe is the only reality, and all phenomena are but expressions of a single unified being. This was the same Einstein who, from the beginning, believed that science not only explained nature, but also helped humanity understand its place in the cosmos. By late 1954, Einstein's heart condition had worsened significantly. Nevertheless, he made a point of attending his 85th birthday celebration at Princeton, surrounded by colleagues and students. A student played Mozart's favourite symphony on the piano, and Einstein, with his gentle smile, nodded along to the music, one of the final moments that captured the genial spirit of the great mind. In the pre-dawn of April 18, 1955, as the first light of morning appeared, Albert Einstein drew his last breath in his small Mercer Street room. The only sound that remained was the grandfather clocks ticking on the wall, reminding all that while time passes, his imprint endures. On his desk lay the unfinished manuscript The Hidden Relations, the ink still bold on the final page, a symbol of his uncompleted wish for a grand unified theory. And so, in the stillness of that Princeton dawn, the earthly journey of Albert Einstein came to an end. Yet from those first drawn circles to the equations that underpin modern physics, his spirit and legacy live on forever in the space-time he helped create. The spring of 1956 dawned warmly across the Institute for Advanced Study in Princeton, where the stone steps still welcomed the morning mist. Albert Einstein's name continued to resonate through Fuld Hall, which regularly hosted Einstein's Spirit Symposia, bringing together physicists, philosophers, and historians of science to explore his great legacy. Space-time maps, tensor diagrams, and his old diaries were displayed with reverence, testifying to the enduring power of Einstein's thought across decades and inspiring young minds to carry on his work. Around the world, on the anniversary of his passing, universities from Tokyo to Cape Town observed moments of remembrance. Students and faculty reread the peace declaration he sent to the United Nations. They recreated his walks by Carnegie Lake to the sound of piano music and breezes through the willow branches. At the Smithsonian, filmmakers produced the documentary Einstein, the narrator of Space-Time, interviewing the last eyewitnesses who worked beside him and reconstructing the quiet sanctuary of his study where he dreamed, wrote letters, and sketched curved trajectories. In the early 1960s, the Einstein Foundation partnered with UNESCO to launch the Science for Peace education program, training instructors from many countries and sponsoring free STEAM courses. The project connected remote regions, geographically isolated, with methodological resources and online lectures, so students everywhere could experience the wonders of light, time, and gravity, the very concepts that made Einstein famous. Meanwhile, there are astronomers using the Planck and WMAP satellites continue to unearth the cosmic microwave background, gathering data on dark matter density and dark energy to compare with the Einstein de Sitter cosmological model he had originated. Each deviation in the temperature distribution charts raised new questions. Might the cosmological constant L, once dismissed by Einstein as a blunder, in fact be the key to today's accelerated expansion universe? At Fermilab, a young research team led by Josephine Nguyen dubbed their extended model Einstein Legacy 2.0, paying tribute to his pioneering work more than 6 decades earlier. In particle physics, CERN's LHC continued the search for the quantum graviton. New data recorded a rare signal reminiscent of the graviton, precisely the quantum excitation of the gravitational field that Einstein once imagined. Though still inconclusive, these hints have spurred theorists to propose more sophisticated mathematical frameworks that unify the weak, strong, and gravitational forces, launching the hunt for the super theory Einstein long dreamed of. Beyond fundamental science, engineers deployed quantum internet networks that exploit time dilation to encode information, ensuring maximal security. Their Einstein secret system, relativistic quantum key distribution, bears his name as tribute. The relativity key not only protects data, but encapsulates the profound connection between light, space-time, and signal transmission, a concept Einstein first sparked in his photoelectric effect paper. Finally, Einstein's greatest legacy remains the bridge he built between science and the humanities. His famous lines, "Imagination is more important than knowledge," and "Education is not the filling of a pail, but the lighting of a fire," continue to be shared. Along research institute corridors, alongside tensor formulas, his quotations hang as reminders. Never stop asking questions. Never sacrifice intellectual freedom. And above all, remember that science is a tool in service of peace and humanity. Albert Einstein's legacy permeates every corner of modern life, uniting theory and practice, science and the humanities. From the equations he scribbled on blackboards, countless world-changing applications have sprung forth. Navigation technology, the Global Positioning System, GPS, exploits time dilation from both special and general relativity to pinpoint locations within meters. Whenever our smartphones connect to satellites, the atomic clocks in orbit adjust for a fractional second difference using delta t equals t naught times square root of 1 minus v squared over c squared e, ensuring that mariners, airplanes, self-driving cars, and even pets wearing smart collars all navigate precisely on the Einsteinian foundation. Gravitational wave astronomy. LIGO and Virgo directly heard the reverberations of colliding black holes and neutron stars, unlocking the space-time window Einstein predicted. We now observe not only electromagnetic radiation, but the very ripples of gravitational waves, revealing the universe's deep structure and directly confirming general relativity's framework. Biomedical sensing. Insights into atoms and molecules, sparked by Brownian motion experiments, have driven advanced biosensing techniques, measuring random nanoparticle motions to monitor protein interactions. The study of atomic flows in fluids now underpins targeted drug delivery systems and ultrasensitive biomedical sensors. Education and culture. Einstein's maxim. Imagination is more important than knowledge has become a guiding principle in STEM education. Students are encouraged to imagine experiments, build model elevators to experience the equivalence principle, and draw wormholes on paper to understand curved space. Interactive museum exhibits worldwide use VR and AR to recreate light bending around massive bodies, letting audiences of all ages grasp relativity through immersive experience. Philosophy and society. His letters and speeches on peace, human rights, and scientific responsibility have become manifestos for nuclear disarmament movements. The Einstein Foundation and the Einstein Prize for Peace and Knowledge continue to fund NGOs, equitable education and science libraries in underserved communities, preserving the humanitarian legacy he left behind. Quantum and global scale quantum networks. 21st century advances directly echo Einstein's ideas about light quanta. Relativistic quantum key distribution, using time dilation for information security, bears his name in every research paper. Meanwhile, Europe's Einstein telescope and America's Cosmic Explorer promise to extend the gravitational wave spectrum, bringing humanity closer to the dream of hearing the universe. Thus, though Albert Einstein has passed on, every stride in science, from navigation systems to gravitational wave discoveries, from cosmological models to the quest for unified field theory, carries his imprint. A lifetime of discovery did not end with the Annus Mirabilis papers. It endures in our technological pulse, in the vision of future scientists, and in humanity's aspiration for peace. Einstein's legacy also powers much of the energy humanity harnesses today. The photoelectric effect, first explained by him in terms of photons, laid the groundwork for solar cell technology. Photovoltaic panels on rooftops, satellites, and the International Space Station ISS provide clean electricity to our planet and beyond, rooted in his 1905 paper, now a symbol of renewable energy. In medicine, relativistic time effects enable precise simulations of X-ray and gamma-ray beams for cancer treatment. High-powered particle accelerators, built on the electromagnetism theories Einstein studied, now direct proton or electron beams along millimeter-accurate trajectories to destroy malignant tissue while sparing surrounding healthy cells. In communications, the laser, producing coherent monochromatic light, traces its lineage to Brownian motion experiments and light-matter interactions. Modern life depends on fibre optics, optical drives, laser printers, and surgical lasers. All possible because light can be controlled via the photon principle Einstein helped establish. Aerospace applications also reflect relativistic thinking. Moon missions and future crewed trips to Mars require calculations of time dilation between spacecraft clocks and Earth clocks to synchronize signals, maintain telecom links, and ensure navigation security. The simultaneity problem he introduced has become a critical criterion in control system and guidance system design. Biomedical positioning technologies, like wrist-worn heart rate monitors and patient tracking devices, use the same atomic clock principles Einstein and colleagues such as Planck, de Broglie, and Schrödinger pioneered. From his work on blackbody radiation and light quanta, doctors can now detect subtle changes in heart rate or blood pressure with extreme precision, warning of disease at its earliest stages. At the cosmic scale, general relativity led to the discovery of dark matter and dark energy, over 95% of the universe's content yet invisible to ordinary light. Observations of supernova light bent by space-time curvature revealed that the universe is not only expanding, but accelerating. This unveiled an unseen component Einstein once considered via the cosmological constant L, now called dark energy. In artificial intelligence, neural network models and machine learning algorithms rely on gradient optimization methods, concepts related to curved spaces and energy functionals in general relativity. Modern image recognition systems, natural language processors, and autonomous vehicles operate smoothly thanks to deep mathematical and optimization techniques that Einstein and collaborators first developed in variational calculus problems. Finally, Einstein's influence pervades popular culture. His tousled hair and kindly smile adorn books, cartoons, documentaries, and musicals. In research institutes' hallways, quotes like, "Stay curious," or "Imagination is more important than knowledge," serve as reminders from the man who turned Earth into a vast laboratory where anyone can lose themselves in the cosmos and find meaning in equations and tensor symbols. Einstein's work continues to resonate powerfully in materials science and nanotechnology. His concepts of particles and waves of light, together with the microscopic measurement methods rooted in the photoelectric effect and Brownian motion research, have led to the ability to observe and manipulate ultra-small scales. From semiconductor chip fabrication to the design of MEMS, microelectromechanical systems sensors, today's sophisticated components in phones, computers, and medical devices all bear the imprint of the quantum theory that Einstein helped lay the foundation for. In the energy sector, general relativity has simultaneously inspired research into strong magnetic fields and thermonuclear plasma. Tokamak and Stellarator mini-sun experiments based on understanding plasma motion in magnetic fields are the first steps toward an infinite clean energy source. The dream of one day harnessing thermonuclear power that Einstein once mentioned in his letter to Leo Szilard. In environmental and climate science, terrain mapping systems using LiDAR and satellite radar, an application of light and electromagnetic waves, allow us to map oceans, old-growth forests and glaciers with an accuracy of a few dozen centimetres. Thanks to these surveys, scientists can monitor melt rates, sea level fluctuations, and forecast climate change impacts, thereby informing conservation policies, disaster mitigation strategies, and ecological balance maintenance. In transportation, super high-speed trains and the Hyperloop project both rely on low-friction principles and high-velocity relativity to minimise drag and energy consumption. Low-pressure tube models allow passenger or cargo pods to travel at near sound speeds safely and efficiently, an idea Einstein initially suggested in his letter to Hermann Weyl about the potential for near-light speed travel if humanity could control force fields. In agriculture and food science, optical sensors and spectrometers, developed from Einstein's theories of photon-matter interaction, now rapidly measure nutrient content, moisture levels, and disease markers in crops. This enables farmers to optimize fertilizer use, reduce chemicals, and increase sustainable yields, a testament to how Einstein's basic science contributes tangibly to global food security. Finally, Einstein's cultural legacy inspires integrated STEAM education, where mathematics, science, art, and technology merge. Students not only learn the formula E equals mc squared, but also practice drawing space-time fabrics in art, perform lens refraction experiments to simulate light bending, and compose electronic music based on photon frequencies. This approach cultivates well-rounded innovators who are both scientifically knowledgeable and richly imaginative, exactly the future of education Einstein always believed in. Thus, Albert Einstein's legacy journey continues unabated. In every machine, every experiment, and every classroom, he travels with humanity, sowing seeds of hope and encouraging us to keep exploring new horizons. Einstein's legacy also shines through the bold international collaborations between scientists and governments today. From the European Union's Horizon programs to the Asia Cosmology Network, cross-border projects embody the motto, "Science without borders." Conferences that bring together physicists, astronomers, molecular biologists, and IT experts to discuss cosmic big data, like the SKA, Square Kilometre Array, with its thousands of radio antennas in South Africa and Australia, demonstrate that the spirit of cooperation Einstein fostered in Bern and Berlin remains more vibrant than ever. In environmental science, modern climate forecasting models use relativistic methodologies to compute the space-time flow of oceans and the atmosphere. Currents such as the Grand Banks and the Gulf Stream are simulated as space-time streams in the ocean, enabling more accurate climate change predictions. By combining supercomputers with Einstein's relativity equations, today's climatologists can map drought months, high wind belts, and tropical storm risks, helping farmers and vulnerable communities to develop timely response strategies. STEM education has entered a new era with Einstein labs at high schools around the world. Students build mini telescopes, simulate gravitational lensing with clear gels, and model nebular orbits using laser beams. These mobile labs not only teach physics, but also spark creativity and teamwork, truly the educational heritage Einstein championed. Next-generation telecommunications also owe much to Einstein. 6G networks, targeting speeds of tens of gigabits, use ultra-fine delay calculations based on relativistic effects to synchronize signals across multiple satellites, ensuring seamless connectivity for aircraft, ships, and the Internet of Things, IoT. As autonomous robots and flying cars become reality, calibrating those signal delays using Einstein's formulas remains fundamental for safety and efficiency. In regenerative medicine, 3D bioprinting of living tissues, from blood vessels to organ structures, relies on wave propagation and molecular diffusion principles Einstein once studied. Leading hospitals like the Mayo Clinic and Johns Hopkins now use these methods to print artificial skin, mini liver tissues, and simulated kidney tubes, opening a future where organ damage can be treated without donor transplants. Finally, Einstein's spirit of skepticism and critical thinking is celebrated by journalists and communicators. Whenever misinformation or flawed science arises, figures like Neil deGrasse Tyson or Alice Roberts invoke Einstein. If you can't explain it to an 8-year-old, you don't really understand it. That quote has become a rallying cry for science communication, urging the public to ask questions and approach knowledge with transparency. With every advance humanity makes, from international collaboration and climate applications to innovative education, cutting-edge telecoms, regenerative medicine, and critical inquiry, Einstein's legacy remains inexhaustible. Each branch of discovery is nourished by the belief that science must serve the common good and honour human dignity. The next chapter will delve into the philosophical dimensions, where Einstein's heritage lights the path for ethical development and social responsibility in the digital age. Einstein's legacy also bears immense value in artificial intelligence and computer science, as today's deep learning algorithms trace their roots to the probability and matrix concepts he and his colleagues once debated. Artificial neural networks now not only recognize images and speech, but also assist doctors in diagnosing diseases from X-rays, help engineers optimize energy use in smart buildings, and offer creative suggestions for music and literature via language models. Every time an AI system learns from data, it performs a profound probability calculation, echoing the quantum problems Einstein once critiqued. In daily life, personal health devices, from smartwatches monitoring heart rate to body composition scales, use optical sensors and Brownian motion principles to collect minute signals and analyze them as real-time data streams. The Kalman filter, tied to relativistic notions of time, effectively removes noise and predicts health trends, warning of strokes or cardiac events before clear symptoms arise. In cyberspace, Einstein's philosophy of never stop questioning guides information security. Whenever a vulnerability or AI-driven threat emerges, experts invoke his spirit of skepticism and scientific responsibility. Organizations such as OpenAI and IEEE have developed Einstein's principles, a code of ethics for AI that emphasizes transparency, fairness, and technological accountability, safeguarding human dignity and privacy. For public education, Einstein Radio and Einstein Podcast draw millions of listeners each year, telling scientific stories in narrative style that bring relativity, field theory, and quantum discoveries to life as thrilling adventures. Augmented reality learning apps simulate space-time itself, letting learners step into a curved universe, zoom in on Brownian motion particles, or instantly observe photoelectric experiments, transforming abstract concepts into vivid, tangible experiences. On the social front, Einstein's example of peace and humanism continues to guide non-violent movements and nuclear disarmament efforts. His calls to never trade life, when denouncing the nuclear arms race, spurred the Einstein-Russell Manifesto, which evolved into international commitments to ban nuclear testing and address climate change, two of today's most urgent global threats. Finally, in the arts, inspiration from curved space-time and light bending around massive bodies has sparked visual installations, contemporary music, and expressive dance. London's Shifting Time exhibition combines light, sound, and movement to let audiences experience a space-time prism effect, as if living inside an Einstein-crafted cosmic map. In the first decade of the 21st century, Einstein's legacy was further cemented by the era of observational cosmology. The Planck and WMAP space telescopes mapped the cosmic microwave background with unprecedented resolution, confirming the universe's primordial superwiggles, the imprints of quantum fluctuations Einstein had first imagined when studying light quanta. These datasets not only validated the inflationary model, but also hinted at a deep connection between curved space-time and the quantum fabric, a theme Einstein began to explore in his Black Notebook, but never fully resolved. Atomic clock laboratories have achieved ever greater precision, approaching the Planck scale, making it possible to test relativity effects in tabletop experiments. By comparing two atomic clocks separated by only a few dozen centimetres in elevation, researchers have directly observed the gravitational time dilation Einstein predicted, demonstrating that Earth's gravity is strong enough to create measurable time differences with modern instruments. This advance carries not only pure scientific significance, but also practical importance for intercontinental quantum communication networks, where flawless time synchronization is critical. In education, the Einstein reflection method has gained popularity. Students don't just absorb facts, but engage in mini research projects, formulating questions and designing experiments to explore relativity or the photoelectric effect. STEAM learning centres equipped with VR/AR technology simulate a virtual universe, allowing learners to stand on a neutron star or watch planetary orbits around a black hole, turning abstract concepts into vivid, intuitive experiences. In 2019, exactly 100 years after the first light deflection test, the global scientific community celebrated the Year of Einstein, with thousands of events in over 150 countries, gravitational wave symposia, woven fabric space-time exhibits, and short science video contests on relativity all recalled the path from Einstein's quiet Bern study to the rich cosmos he revealed. Today, as artificial intelligence and quantum computing advance, scientists continue to pursue Einstein's dream of unification. New proposals in string theory and quantum optics in curved spacetime show that much remains mysterious. Yet regardless of where those efforts lead, the modernization of science remains bound to the spirit that Einstein embodied: the courage to question, to imagine, and to experiment. As he wrote, the important thing is not to stop questioning. Einstein's legacy is not only etched into the material world, but also deeply woven into humanity's thought and spirit. Culturally, the image of Einstein, his wild silver hair, gentle smile, and profound eyes, has become an emblem of creative freedom and knowledge without borders. Many science museums, from the Smithsonian in Washington to the Deutsches Museum in Munich, feature dedicated Einstein World galleries where visitors interact with 3D models of curved space-time, simulate photon motion, and explore advanced relativity experiments. In primary and secondary education, STEM and arts teaching methods inspired by Einstein are ever more widespread. Students don't just solve Lorentz transformation problems, they also take part in art projects like Universe on Canvas, hand-painting fabrics that depict space-time curvature under gravitational effects. Through this, they learn that science and art are inseparable partners, bringing together beauty and logic. On the societal front, Einstein's principles of scientific responsibility and peace continue to resonate. Organisations such as the People's Science Association and the Scientists for Peace Network advocate for ethical science policies that balance technological advancement with human rights protection. Whenever they hold an Einstein's Legacy conference, talks on climate change, energy sustainability, and social equity always echo his reminder: science is truly valuable only when it serves the common good. In media, educational podcasts and video channels like Minute Physics and Kurzgesagt use Einstein's image and quotes to make complex knowledge accessible. They recount the development of relativity, explain the photoelectric effect, and visualize black hole perturbation experiments with 3D graphics, creating a style of science storytelling that is both accurate and engaging, igniting curiosity in audiences worldwide. Philosophically, Einstein sparked profound dialogues about the nature of truth and the limits of reason. Social science and philosophy journals, Philosophy of Science, Science and Society, and others still quote him. Imagination is more important than knowledge. Articles on unleashing creative thinking, confronting deep theoretical layers, or the trap of narrow specialization all encourage returning to the original Einsteinian spirit. Always ask questions, always dream beyond current boundaries. Finally, his humanitarian legacy, love of peace, compassion for others, and faith in the future remains a beacon in these turbulent times. Each year on Einstein's birthday, non-profits host Knowledge and Hope Day, combining memorials, scientific symposia, and community events to spread his message. Knowledge must go hand in hand with responsibility, and even the smallest contribution can help make the world a better place. The artifacts of Albert Einstein are preserved and displayed in museums, archives, and research centres around the world, each piece a vivid marker of his journey through space-time and his profound human vision. Ulm Memorial, Germany. The 1884 brass compass that first let Einstein draw perfect circles is enshrined in glass. This simple tool not only recalls his youthful passion for geometry, but reminds us that every great idea begins with a single line on paper. Einstein House Museum, Kramgasse 49, Bern, Switzerland. A replica of Einstein's blackboard, still dusted with chalk formulas: G mu nu equals 8 pi g over c to the 4th times t mu nu, stands alongside his rough notes. Visitors pause in silence before the slanted script, sensing the excitement of the moment he first unveiled general relativity. Hebrew University Library Archives, Jerusalem. Over 43,000 pages of original diaries and correspondence are meticulously stored. In the Einstein Archives Gallery, his 1912 black notebook, open to the first page of pencil sketches on the equivalence principle, testifies to the turning point that led him to the idea that a freely falling person feels no gravity. Smithsonian Institution, Washington, D.C. The violin case Einstein carried across Europe is preserved here. Next to it, photographs capture him playing Ave Maria at scientific gatherings, symbolizing the interplay of science and art in his soul. Einstein Museum, Max Planck Institute, Berlin. The Mont Blanc fountain pen with which he signed anti-nuclear letters, including his famous 1939 letter to President Roosevelt, is displayed beside the first printed copies of the Russell-Einstein Manifesto. This artifact reminds us that great scientists bear responsibility for humanity's fate, not just laboratory work. Einstein Memorial Room, Fuld Hall, Princeton, USA. The original Annus Mirabilis manuscripts, his 4 1905 papers, are arranged in publication order, alongside his Nobel Prize medal and invitations to speak at international conferences, tracing his path from patent office clerk to science's highest honour. Each relic, be it the humble compass or the august field equation manuscript, carries deep meaning, the spark of curiosity, the witness to theoretical revolutions, and an eternal reminder of Einstein's ideals of intellectual freedom and social responsibility. Personal artifacts: the Exploratorium, San Francisco, the patched wool jacket Einstein wore at the 1927 Solvay conference hangs on display. Its visible mends testify to his disregard for appearances, caring only for the substance of theoretical debates. Visitors sense his modesty and total focus on science. Center for Jewish History, New York. His Hebrew book box, always carried on trips to Jerusalem, remains intact. Inside lies a small notebook in which Einstein transcribed a German poem by Goethe, revealing his love of literature and original Freiheit. Language: Princeton University Museum, Princeton. The plain wooden desk where Einstein drafted his 1947 United Nations letter on nuclear disarmament stands next to his handwritten essay, Science and the Common Good. The red-inked blotches on the desk cloth evoke the moment he used knowledge to condemn violence. Einstein Museum, Tokyo. The armchair bed where he lay reading and reflecting in his final years is recreated here. Guests step into his Princeton bedroom, feeling the serene yet contemplative atmosphere that nurtured his last great unification ideas. Finally, Einstein's digital legacy, over 80,000 digitized letters, papers, and photographs, lives on in the Einstein Archive online. Anyone can search by keyword or date, accessing his original writings and experiencing the spirit of his era through his own words. In the digital age, Einstein's dream of universal, borderless knowledge has become reality, ensuring that humanity will forever preserve and learn from one of history's greatest minds. And so the portrait of Albert Einstein's legacy is completed by both tangible and intangible pieces, from the small compass to the manuscripts that reshaped space-time, from the simple wool jacket to the pleas for nuclear disarmament, all preserved in museums and archives across 5 continents. Each artifact is not merely a trace of a gifted individual, but an endless source of inspiration for anyone who stands before a glass display case, pauses over a diary page, or gently touches the old violin case, to feel the breath of science intertwined with the human spirit. The journey, from the boy drawing circles with a compass to the theoretical genius, from his first days in Ulm, Bern, Zurich, and Berlin to his final years in Princeton, concluded with his passing on a peaceful spring day in 1955. Yet Einstein lives on in every equation, every letter, and every artifact he left behind. He did more than bend light. He opened the way for humanity to bend its understanding of itself and the world. When we stand before a blackboard chalked with E equals mc squared, or gaze at the desk cloth stained by the red ink of his peace letter, we realise that science is not merely dry calculation, but a story of aspiration, responsibility, and compassion. Einstein handed the world a flame, the flame of curiosity, of daring to question, and of faith in the power of education to build a better future. Thus, this 9-chapter, 27-part journey ends in triumphant celebration of knowledge and humanity. Albert Einstein's legacy, from his objects to his ethos, from science to the humanities, will forever accompany us on our voyage through space-time and our quest to fulfill the greatest of dreams.